Hi to all, thanks to RSS for inviting me. My name is Massimo, I'm from Bologna University. This is joint work with Daniela Cocchi from Bologna and Maria Scott from Glasgow University. So my main research topic is on modeling spatial datasets. So today I will give you a proposal for modeling land use maps. And what are land use maps? So we talk about what these maps are and a case study that we will look at, an approach, statistical modeling approach for this data, one parametric approach based on smoothing, and then we will look at some inferential procedures which can be applied to this data and which can be perhaps useful for urban planning purposes. So what are land use maps? So this is an example. This is Bologna, and we have a map of polygons. Each polygon is assigned a land use type, a land use label. So for instance, here I put these polygons which are red represent residential urban use. For instance, the blue ones are polygons where it has been observed commercial urban use. Yellow is agriculture, and green is forest. So this gives you also an idea of the metropolitan area around Bologna and the morphology of the area. So we have here some small mountains here in this area and almost flat in this area. These are the direction of the roads. This is a road and also a railway here in this direction, which is the Via Emilia. And also we have this other direction. So this is a sort of idea of the pattern. So what land use maps gives you idea of the distribution of land use over space. And what you can do, you can look at this map, and you can also compare this map across different times to have an idea of the dynamics of the urban growth. This data actually, so this is another pattern, it's just selection of the polygons characterized by urban residential use, which is actually the kind of land use type that we are focusing on the case study part of this talk. So we see some fragmentation, some sparseness of this pattern. So this is the most recent data set that we got from the cartography archive of Emilia-Romagna region in Bologna. And this is for 2008, I think. So actually what we can do is an inspection. And what actually these maps are they derive from post-processing of remote sensing images. So there is lots of techniques to transform remote sensing images into maps of polygons which are easy to understand to the public and are produced by institutions at local or international scale. There is one standard of classification very popular, which is the one introduced by Corinne Cover Program by the Environmental European Agency, which is a standard to classify polygons. So we have I think like more than 40 land use type categories that you can assign to polygons. So it allows you to create very rich maps. But for statistical purposes, what you have to do is to rasterize these datasets. So here is a toy example. What you have to do, you have maps of polygons. So it's a road, buildings, for instance, and you have to transform to these maps of polygons to this grid structure dataset. And this is very useful. This is easy to store because this is just a matrix of numbers. And this is very, very expensive to store because you have to collect in your dataset all the information on the boundaries, and it's also difficult to analyze. You can do less things in terms of summarizing the phenomenon. And here you can compute many indexes. You can also apply statistical modeling because you have lots of statistical models for lattice data. And so this is what you need to do to start thinking about applying statistical modeling with these maps. You have one issue. The first issue is to define the grid resolution. You have to fix a grid resolution. So the finer the grid resolution, the better in terms of representing the spatial pattern. But of course, you might end up having too large matrices. You can't do computation anymore. So you have to fix grid resolution, considering this trade-off between representation of the pattern and computation of visibility. And another important issue is which criteria to use to assign a value to the grid box. So the most typical thing to do is to assign, for instance, this grid box to, say, urban use, if the centroid of the pixel is covered by that type of urban use, so by urban use. And another criteria could be to count to divide the pixel in sub-pixels and to count how many of them are covered by urban use. So in the first case, we will have binary data. So either urban use or not urban use. So 0, 1, so black-white patterns. And in the second case, you will have sort of intensity map. So you could assume binomial counts instead of Vernonian observation in terms of statistical modeling. So here is the data set that we actually use. It's data from the cartography of Bologna. We selected residential urban use because we are interested more into studying the urban sprawl effect, and this is very much related to where people live. If people live all together, it's convenient for society in terms of infrastructures and services that you have to provide to people. If they are spread around, it gets more inefficient. So urban sprawl is a name to characterize this situation, at least in the urban literature. So we got this data set. We selected the polygons we are interested in, so urban residential use, and we rasterized the data, assuming a 0-1 representation. So black is urban, residential, and non-black is non-urban, so it could be anything else. And in this case, we plot this data on an elevation map, just to give you an idea of the morphology of the area. And elevation is also a covariate that we use in our modeling approach. So here is just a plot of the pattern in the different years. We got data from 4 time points, and we have 1976, 1994, 2003, 2008. And these data show a little bit, gives you an idea of the kind of sprawling that is affecting the area in the last, say, 20 years. And also it gives you an idea of the polycentric nature of the urban pattern, because here is Bologna. The municipality of Bologna is about here. And then we have a neighboring municipality which creates other centers. So if you consider the metropolitan area, you have many centers, and you can spot them. And we want something also to make spotting them easier. And so what we consider is, we give a look at the literature. We have topics in the literature that can help us. One is urban sprawl indicators. This gives a single numerical summary for the whole metropolitan area, and these indicators are able to capture the morphology, discontinuity pattern, and so that's why they are called urban sprawl. But these are too poor in representing the pattern. Actually, to give you a number for a big area, so we did some work in the past with those, but then we want to do something else. We want to detect the changes and detect trends in these maps. So very, very big topic in the literature is traditional land use change detection. But this is based on analyzing remote sensing images. So you need to have a lot of experience in this remote sensing thing. And what they do actually is comparing the maps of reflectance values. So basically what you can do with these techniques is to analyze changes at the pixel level. So you get the increased pixels. So you actually are only able to detect changes at the spatial scale, which is determined by the data itself, by the resolution of the data itself. But there is also an approach to smoothing these remote sensing images and detect larger scale data at a scale, spatial scale, which is larger than the resolution of the data. And I think this is interesting, and I think this is perhaps more useful for urban planning purposes. The importance of the spatial scale of the change, detecting small scale change, say at the pixel level, which pixels are increased in urbanization, or detecting versus detecting large scale changes, so at a larger scale level. And perhaps urban planning, since it operates at a metropolitan scale, it's perhaps more looking for large scale trends, changes, rather than small scale. So what we want to do is to analyze the spatial trend underlying the binary raster map that we created and detect the regions of change. And so regions which are more urbanized than a reference level, and or regions characterized by an increase in urbanization with respect to a reference time. And we propose a smoothing approach, so a modeling, a non-parametric modeling approach, where we consider we consider y at pixel I and time t as the Bernoulli distribution, and the probability at each pixel and time, probability of urbanization. We want to model it as a something varying smoothly over space. And so what we do is we make use of some important covariate to help to predict the pattern, and covariate we put it here, and some fixed effect of this covariate, and we use elevation, but we could use many other covariates that we think are related to the residential urban pattern, and then a smooth effect, so a surface varying smoothly across the pixels. And we model this with Bayesian p-splines. And what we do is to assume a surface at each time, so that partial effect can vary at each time, and we have 4 times. What is Bayesian p-splines is shown here. People who are not, for people who are not familiar with this, is a method to estimate a smooth effect. In this case, estimate a smooth surface. So what you have to do is to use a b-splines basis. So this is a basis made of equally spaced b-splines, which are these little caps here, and it is basically a regression on this basis of b-splines, and a regression in a way that some smoothness is forced. So it's a regression on this basis. We have a spline coefficient associated to each b-spline, and you achieve smoothness basically by putting a smoothing prior distribution on these coefficients. And this is a standard approach. It's a quite well-established approach, which is numerically stable. And what you actually are assuming here is that there is correlation between the coefficient regulating the size of this b-spline, so that the first surface turns out to be smooth at the end when you estimate these coefficients. So it's a good method for smoothing, and it's good because these b-splines are local, so it's you have good numerical properties for this. And then the smoothing prior that you assume is actually a Gaussian Markov random field, and so it implies sparse precision matrices, so you can get also efficiency in estimation because you can use sparse matrix computations. You can implement a Gibbs sampling. What we did is implementing a Gibbs sampling and using an augmented approach to treat the fact that we have binary data proposed by Albert and Chibo. You can use some trick to speed up things and get efficiency, block updating on the spline coefficients, a sparse matrix computation with this very useful package. But also, actually, you can avoid programming the MCMC yourself, and you can use available software that are now available and also quite well documented and easy to use. So you can also think about using this it's at the level of like in an agency, like users in an agency could be able to implement this because there is software and to fit Bayesian T-splines. For instance, the R-inner package and BayesX software, all well-tested softwares. And then I want to show some results of our model. So this again is our dataset, just to remind the pattern. And here is the estimated spatial trend. What we actually have during estimation, we can build an MCMC sampler at each pixel of the posterior distribution of the surface. And you can imagine this surface as the probability of urbanization surface, or if you want, the residential density in the probability scale. And so this is the smooth pattern. In this case, we choose quite a rough B-spline grid, one B-spline, so one of these bell-shaped function, each around 5 kilometers, and you get this smooth pattern, which gives you an idea of where are the spot of urbanization. And if you are finer in the grid resolution for the B-spline, say one B-spline is 2 kilometers, you get, of course, a finer representation of the pattern. Because there is also information of the small scale that you can capture. So in principle, if you use very many B-splines, you could really pick up all the small little change features in the data. And here is another representation with another finer grid. So this is a sort of a thing that you could use a geographic criteria to impose this number, and you can play with it according to which is the spatial scale of interest for you. You want to identify changes at a scale of kilometers, then you can adapt your choice for your interest. So what we actually do for inference, as I said, we have available an MCMC sample at each pixel and at each time. And we can do many things actually. We can compute the mean, so we can plot the posterior mean, which is the plot that I showed before. And then you can also make inference because you can compute quantiles of the distribution. So what you can do is that you can, for instance, isolate high urbanized regions by assuming a reference level. So you may assume 50% as a reference level for urbanization and check which are the pixels which have a distribution that is above this reference level. Because you can do inference because you have an MCMC sample of the surface. And also you can compare different times. So you can compare surfaces and you can see which pixels are, in which pixels we have a separation of the two surfaces. So in these cases, we will have a pixel which is increased in urbanization at now, for instance, with respect to a reference time in the past. So we will show you this sort of analysis now. But this is the first idea. So taking a reference level, for instance, 70%, and emphasize or isolate the area that are higher than 70%, which are the area included in the red lines here. So red lines are contours in these maps. But since you have an MCMC sample, you can estimate also the uncertainty of these contours, which are the blue area around the contours. So you can do these things. And in this case, this particular case, this is 2008 and this is 1976, you can see probably more easily the polycentric nature of the area. You can see, you can locate this center here, here, here. And sometimes you can find out interesting things. For instance, this municipality here has two centers according to this criteria of selecting high urbanized area. Also, if you want to have a visual comparison present and past, you can give a look at it, and you can see how in the last 40 years the city has sprawled in the metropolitan suburbs, and how things are very different nowadays with respect to the past. How this direction have developed, how this direction has developed. So if you change the reference, you say you take a lesser reference, 50%, you can still apply this. You can see this as an arbitrary parameter that you can change for urban planning purposes. And you can see other things. Of course, if you are less restricted, you see a more sprawl pattern. You identify more possible centers that an urban planner could think to take care of. Okay, so this is just a visual comparison between types, but here is a method to make a formal comparison, because we take the surfaces and we compare these surfaces. When they match, actually there is no change. When they separate, there is significant change. So for instance, here is the pattern. This is a comparison, again, 2008, 1976, and we fix a credible level, 90%, and we have the red pattern is the data at 2008, and the black pattern is just superimposed here to this data, and is the pattern in the past, 1976. And the green area that you can see here, are the result of inference that we are doing. So here, this here is well separated now with respect to the past. So this is an increased probability area. So the residential density here has increased. We can depict the border of this increase. We can do a little bit more than just checking the pixels that have increased. We have a whole region that has increased. And also it's interesting to note that maybe the next is a less restrictive criteria. So here we use a less restrictive criteria, 80% increased probability. And so we see, as we are less restrictive, we see higher increased region, larger increased region, sorry. And if we are less restrictive, again, we have larger area, so 60% increase in this area. And we can analyze, for instance, has some area has grown around an existing area, for instance, this municipality here, and also these, or perhaps this area. But some area is just new area, like these areas, or these areas. And so this perhaps could be a useful tool for planning, perhaps to decide where to build new urbanization, where it's more convenient to build new things. Perhaps it's more if you have to build new things in these areas, perhaps more convenient to build it here, since it's just well urbanized, rather than here, so that you don't spoil free land. I don't know, it's probably very naive consideration, because maybe there are so many implications in decision of this type. But yeah, this is just an example of how you can use land use maps available to the public to make some analysis which could help in urban planners. So just to recap and conclude, so we use land use maps which are widely available and produced by many institutions. Actually, we use local kind of data set, because it's a data set that we took from Bologna cartography, so it's not the European Environmental Agency, but you could use many data sets, because it is a wide availability of these maps. Then you have to rasterize the map, and you produce a binary urban pattern. You can do modeling on this, and the smoothing is nice in this case, because it gives you the chance to detect changes at a larger scale, and you can sort of fix the spatial scale that you want to analyze, as opposed to changed pixels. So we sort of are more interested perhaps in low intensity changes, but at a larger spatial scale, rather than high intensity changes at pixel scales for urban planning purposes. I have to say that we use this approach to Bologna dataset, to Bologna city, that it's not an extremely rapid environment in terms of urban growth. It's an historical city. There is not much going on in terms of increasing urbanization, but perhaps these tools are more useful for rapid growth environments, so cities that sprawl very quickly, where you perhaps can see changes at a scale, temporal scale, which is lower than 40 years, which is the sort of spatial, the sort of temporal scale that changes occur in Bologna. And so this is the main idea. And much work to be done on the statistical side in terms of model validation, choices of priors in Bayesian P-splines, which is an interesting research area, and especially in doing the simultaneous inference instead of pixel-wise inference. So actually what we are doing is something very basic at the moment, pixel-wise inferences. We are not taking into account the multiple testing issue that is involved in this. But there is lots of literature to solve this issue, so this is for future work. So I'd like to stop here. Thank you for listening.
Thank you very much, Massimo. So, who has questions for him? Stunned in silence, is it?
Just a quick, easy question on your graph. It looked like some areas have actually gone the other way, some are more urban historically than they are now. So if you switch the colours on some of those graphs, you could identify those that have gone the other way, which personally I think would be quite
What do you mean? Sorry, in the other way?
Some of your graphs, if you look at one of those graphs, which is, if you go to one of the other ones, which shows the history, some of the earlier graphs, we had 4 where you showed, maybe...
The data set?
Yeah, that one, probably that one. It looks to me like some of the central areas in 1976 are less urban in 2008.
Okay.
So if you switch the colours on your later graph, where you had the black and the grey, you could see which areas were more urban in 1976 than they are in 2008. Which,
are you talking about
yeah.
This area?
Yeah.
It's the northeast.
Yeah, and where you just pointed to be honest. It looks to me like...
So it's like this area here
Yeah.
compared with this area.
Yeah.
Oh, yeah.
Not here.
Yeah.
I think that's
Also-
us to do, I think that has to do, that's also one reason why we think smoothing is good in this case, because actually the classification standard has changed between this and perhaps this map, or probably also between this and this. So that means that actually the standard to create this map was different 30 years ago than now. So it's probably at the data level is not comparable with the situation. So probably this is sort of artifacts, because here we have many land use classes. We can really select the urban use that we are interested in, which is residential, but here was different. Probably residential was mixed with other urban use. So smoothing allows you to make this issue less severe, because what you're interested in is in the large scale changes, so you can remove these sort of small scale things. But you are right, in principle, it could happen that something that was residential urban use in 40 years ago nowadays is not, because it could be commercial, for instance. It could have been turned to another use. So it's difficult that it was turned into agriculture, because you have to, it's a long process that, but it could have been turned to another land use type. And here we are looking at the residential type only. But it's also an interesting question in terms of modeling, because urbanization, one can think, can only go in one direction, from nothing to to urban, and the other way around
It would
is
be quite easy because you just need to switch the colours on your later map and you can see straight away the areas which seem to have gone the other way, you know, which is quite, I find quite interesting.
Yep. Thank you.
Thank you. Any other questions? Thank you. Out the front here.
Is there a way to summarise the information you have in those 4 pictures there into a number? So you could, I don't know, by looking at the frequency and distance of occurrences of new residencies in regard to the centre. Just because for me, like looking at 2003, 2008, just kind of comparing them visually, it's hard for me to kind of see if there's any sort of definite change. But if you summarise it into a number, you can say, oh, there's been a sort of
yes, you can,
0.2.
for sure you can. Yeah.
Yeah.
You can estimate the probability of urbanization as the proportion of urbanization in the whole area just by taking the proportion.
Right.
You can produce single numbers, but perhaps you could, to do what you want to do, perhaps you could produce these maps, but with a comparison between 2008 and 2003. So this is not a number, it's a map, but it can give you sort of idea of where are the differences that you cannot see by eye, but maybe using a testing procedure you can spot the difference. But yeah, for sure you can also calculate summary with.
Great, thank you. Any other questions there, please?
Well, how do you do the rasterisation? So you talked about the spline fitting, you gave packages for that, but is the rasterisation easy?
The rasterization, I did it using the raster package in R,
Okay.
which is quite
Easy, yeah.
well developed, yes.
And just looking at the future, you're saying there's a number of challenges to this work, which you're talking about in terms of model checking priors. Are these areas of work that you're going to carry on working with, or are you looking for input
Yes,
into?
in particular I'm working in the checking the prior and working out prior which you can use to inform the model. So at the moment the research line that we are focusing is more into working out the prior for this prime model, and but also looking at the ways to solve the pixel-wise inference issue would be nice, because actually what we are doing here is something too restrictive perhaps, because if you want really to see to be able to state that all this area is 60% higher now than in the past, you would really need to consider the multiple testing issue that you have here. What we can say now is that each pixel in this area happens to be higher than 60%, but not really that the whole area is higher than 60%. And there are statistical, there is work in the literature nowadays, like excursion sets to check really when a spatial field is higher in certain area, and so this is something that we could apply in the future.
Okay, great, thank you. Well, so thank you very much, Massimo. I think that's all the questions. We'll move on to our second speaker. So let's